So this is the second session, right? John Hughes is going to talk about understanding formal specifications through good examples.
Okay, thank you. So this is work done with lots of other people. That's me. But let's get started. So I want you to imagine for a moment that you're not already familiar with the airline process registry. I'm talking about these three functions: register, unregister, queries. So suppose you don't know what they do and you want to find out. How are you going to do it? Well, you could read the code, of course. It's about 600 lines of C, and you can fit it on 2 slides in a 2-point font. But it's full of implementation details that you don't need to understand just to know what these functions do. So that's not a very good idea. Wouldn't it be much nicer to read a formal specification of these operations? And we have one. This is a quick check specification. We can use it to generate random sequences of calls to the API and to decide whether or not they're behaving correctly. So this captures everything about how these operations should behave, but there's no implementation detail. But it's 130 lines, so that's not super short. Maybe to begin with, you might like to look at some examples instead. Would you like an example?
Yes.
Here's one. Here's one thing you can do. You can spawn a process. I've got a function spawn that just does that. And then you can register the PID. We'll register it with an AMA, and then you can call queries to look it up. And if you do that, and you run this code, one of the things that you might see is these results. So spawn is return to PID, register, return true. And when we call queries, we get back the PID that we registered. So this is how I'm going to show you examples, with code on the left, and then the results of a sample run on the right. And I think this example already gives you a very good idea of what register and spawn are supposed to do, right? Interestingly, when we run this example, it covers 58% of the formal spec. So you would have had to have read and understood about 80 lines of specification in order to predict what would happen in that simple case. Cutting that down to 3 lines, that's a big win in understanding. But of course, one example isn't enough to tell us all we want to know about how these functions behave, so let's look at a few more. Here's one. You can register processes, certainly, but you better not register them twice. Because if you do, the second call to register will raise an exception. And I'm showing that just by giving exit bad arg as the return number. But it represents an exception. So don't register the same PID twice. Actually, you better not reuse a process name either. That also results in an exception. Once you have registered a process, you can unregister it again. That returns true. And once you've unregistered it, queries will now return undefined instead of the PID. Just like register, you better only unregister once though. If you try and do it twice, you get an exception the second time around. But what you can do, once you've unregistered a PID, is register it again. This time, perhaps with a different name. Okay, so now you've seen a number of examples and I've given you a little explanation. And the explanation I gave you, of course, I made up myself. The interesting thing here is that I did not choose those examples. Those examples were generated and selected by the method of the paper that I'm talking about. So why have we done this? Well, formal specifications are actually often hard for people to understand. For example, we built formal specifications of our basic software for Volvo cars. And that was 20,000 lines of airline code. So, you know, the customer may want to know, what does your specification say? You can't say, here's 20,000 lines of airline, which you don't understand. You figure out what it means. Of course, you have to be able to interpret it. And being able to generate examples that illustrate what the specification means can be useful for explaining what it says to stakeholders. But actually, it's also useful for the developer of the spec. After all, does the developer of a 20,000 line formal specification necessarily understand exactly what it says? No, probably not. So if we can generate good examples, that may be helpful to the developer too. So here's the question that we're trying to answer in this paper. How can we generate examples of API usage that will enable a person to understand its behavior. Okay, let's think about that. Let me describe our approach. We consider that every example should make a point. Right? You don't want just random sequences of API calls, they're not interesting. When you see an example, you should know what it's telling you. And moreover, every example should be minimal among the examples that make that point. So each example should contain precisely enough to illustrate the point that it's making and no more. So how can we possibly generate these things? Well, we're going to use quick check. We're going to generate lots and lots and lots of random examples, classify them according to what point they make, and then once we've found an example that makes some point of interest, we're going to use quick check shrinking to get a minimal example that makes that point. So this is actually quite easy to do. All we have to be able to do is to say what point a particular example is making. So let's come back to the very first example I showed you. What point is this making? Well, we have a heuristic that says that examples are interesting because they illustrate interactions between calls in the sequence. And we claim that in this example, the register call interacts with the subsequent call to queries. How can we tell that? Well, so we're going to classify this as a register queries interaction. And that means in our suite of examples, we're going to generate one example of a register queries interaction. How do we know they interact? Well, suppose I didn't make that call to register. If I remove the call, then the result of queries would change, right? But looking to see whether the result changes when you remove the call, if you rerun the test, it doesn't work, because the result would change if I reran the test with no modifications, right? Just because we get a different bit. So what I need is a way of telling that register affects queries without rerunning the test. And for that, we have the formal specification. Look at this example. It can't happen. But why can't it happen? Well, obviously because queries won't return a PID if you haven't registered anything. And the formal spec says that. The formal spec tells us that this can't happen, and therefore, without rerunning the test, we know that the call to register must have affected the later call to queries. So, that's great. Now, this heuristic, that we can show that one call affects a later one, explains almost all of the examples that I showed you in the introduction. The one thing it doesn't explain is why we saw both of these examples. Why? Because they're each register-register interactions, right? So why have I got two register-register interactions? Well, it's because of the repeated values. So in the first case, we're repeating the process identifier in both calls. In the second case, we're repeating the process name. So we abstract away from the names, from the argument values, when we decide what an example illustrates. That's because we don't want to generate an example of registering a process with the name A, and an example of registering a process with the name B, and so on. So argument values generally don't matter, but we've observed that often repetition of values does matter. And so what we do is we don't call this a register-register example, we call it a register underscore A, register underscore A interaction. And this A is a meta variable that just has to be the same in both places, whereas underscore can be anything. So that, of course, this then will have a different description, and that's why we get both examples in our example suite. We have a few more heuristics as well. Here's another example that we generate for a different API. This is for the API we use in our evaluation. It's a banking API. You can create users. And this example shows that you can create more than one user with username U1 and U2. Why is it included? Well, it would not be included using the previous heuristic, because if I remove that first call to create user, it doesn't affect the result of the second call. Right? So that there is no create user interaction in the sense that I described previously. However, if I modify the argument of the first call to be the same username that I use later, that actually, in this case, causes the second call to fail. And so, in this example, I know that the arguments of the call affect the result of the later one. Well, we use that as a heuristic as well to generate examples in our example suites. Here's an interesting one. This is from the debts API. So, this example opens the file, inserts a tuple, and then calls lookup. And clearly there's an insert lookup interaction here, right? The call of insert affects the result of lookup. But now look at this example. Okay, so here I do the insertion, I close the table, I reopen it, and I do the lookup. So this also is an insert lookup interaction, but it's not minimal. And so therefore, quick check will remove the close and open from it. And we get the other example, but not this one. And what we found was that seeing the other example didn't enable people to predict what would happen in this case. Because they weren't sure whether or not the contents of the table would survive being closed and reopened. For debts, of course it does. If you did the same thing with ets, of course you'd lose the contents. So people weren't able to predict that. And that shows that we really need to include this example too. But it's a different kind of example. So we actually classify this as a close lookup undo interaction. What does that mean? So in this example, the close would change the result of lookup, in fact, would make it erroneous. But the open undoes the effect of the close, so that now we can perform the lookup successfully. And it's quite interesting, actually, to find examples where you do something in a sequence of API calls that changes the state, and then there's maybe a sequence of things you can do afterwards that restore the previous state, generating examples that show how to undo actions we've also found to be interesting. Okay, so we have these heuristics, we use them to generate suites of examples. Let me come back to our research question. How do we generate examples of API usage that enable a person to understand its behavior? How can we tell whether our examples enable people to understand anything? Well, there's only one way. Human experiments. And so we have subjected humans, students of course, to our examples. We gave them generated examples, and then we measured how well they understood the API. How can you measure that? You can't look into somebody's brain. What we did was, we gave them tasks to perform. And the tasks looked very like the examples, except that we omitted the return values. So we argue that if somebody can correctly predict the return values from sequences of calls, they must understand the API. Or at least, we're going to measure their understanding in this sense. And so we can get a percentage understanding out of this. We just measure how many answers the student gets right. And this, by the way, is one of the tasks that we gave students. And it's using a toy bank server, in which you can open the bank server, you can create accounts and users, you can log in and log out, you can make deposits and withdrawals and so on. There's 9 operations in the API, and the model is about 250 lines of code, so it's about twice as complex as the registry. It's small, but it's not trivial. So our experiment gave students a set of examples and a set of problems, and we could measure how well they answered them. But of course, there's still a problem. Suppose the students get 80% of the answers right. Is that good? Or is it bad? It might depend on how hard the problems were. So in order to know what we're measuring, we have to have something to compare against. And first of all, we thought, well, let's give them completely random junk. Then we thought that's not very fair. So instead, we thought, what would a plausible alternative be? We generated, by the same kind of method, a minimal suite of examples with 100% code coverage of the implementation and the spec. And now, that's quite plausible, isn't it? You might say, well, these examples, they exercise every part of the code and the spec. You must be able to understand, perfectly from them. That sounds kind of plausible, doesn't it? Well, that using that method on our case study generated 22 examples. Using our heuristics, generated 55. So you can already see that our heuristics demand a bit more of the examples than 100% code coverage. Now, I'm saying here, in this case we get 22, in that case we get 55. Of course, there's some randomness involved in generating these things, because the search for interactions is random. So you might wonder, maybe I was just, unlucky this time to only get 22 examples and lucky to get 55. But no, because remember, we're generating examples and then shrinking them. And that shrinking process removes all the irrelevant stuff, and the results of this kind of search are very, very consistent. So if I generate examples, in this case several times, I'm going to get probably 22 examples every single time, and they'll be very similar. They might use different names for the registry. There might be some examples where there's a couple of calls that could appear in either order, but they don't vary more than that. So these results really are very, very consistent. I am comparing, making a sensible comparison. So then we had 22 students. We divided them randomly into two groups of 11 each, and we gave them 7 tasks to solve. And here are the results. It's a box plot. And these show on the x-axis the task numbers. So there were 7 different tasks. And on the y-axis, the percentage of return values that the students got right. And the white boxes represent students who got examples with 100% coverage. The grey boxes represent students who got our good examples. And you can see that for every task, the grey students did at least as well, and very often better, than the white students. Indeed, overall, the students who got our good examples got a 16% higher score than the students who got 100% coverage examples. Okay, so you might wonder, were we just lucky? Well, we were lucky over 7 tasks, but the whole experiment was 22 people, 15 minutes. So, maybe you can be lucky for 15 minutes. So, of course, we have to apply statistical analysis to these results. And we did so. We used a repeated measures ANOVA test. Look in the paper. To try and answer this question. Do the subjects perform better given examples generated by our heuristics than they do given examples with 100% coverage? And the answer is definitely yes, they do. Whenever you apply this kind of statistical test, you get out a p-value. In this case, it's 0.005, which is really small. So this means even though we only have 22 students, we can be 99.5% certain, or confident, that the good examples really do help more than the 100% coverage ones. So that's a good p-value from a human experiment. And another thing you can do is you can measure the effect size. So how big was the effect of getting good examples rather than coverage-based ones? It was 0.33. What does 0.33 mean? Well, luckily, you can look in papers that tell you how to interpret 0.33. And the interpretation is large. So we're 99.5% confident that we observed a large effect. So that's great. Okay, so of course we're not the first to try to generate examples of how to use an API. In general, the previous work has tried to extract examples of usage from a corpus of code. So that makes sense. You can see how APIs are actually used. But there are a lot of problems in that approach. So one problem is that in real use of an API, the functions you're interested in are going to appear, but there'll be a lot of irrelevant stuff as well. So to get good examples out from a corpus of code, you have to be able to simplify. And that's a tough problem. People have used program slicing, static analysis, and so on. It's quite difficult. All we have to do is shrink the examples. QuickCheck already does it. Really easy. But the other thing is, I showed you some negative examples. I showed you things you should not do because you'll get exceptions. And we can generate those from the spec quite easily. But you're unlikely to find that kind of sequence in a corpus of real code because, of course, people will avoid it. So that's also an advantage of this approach. Well, so what do we see? I want to emphasize that formal specifications are inherently quite difficult to understand. I think it's a bit too easy, perhaps, for people to say, it's a formal spec. It's obviously very clear. But that's not true. If you have, 20,000 lines of spec, it's difficult to understand. Good examples are invaluable for understanding what spec says or understanding what code does. And it's no wonder mathematicians have been using examples for centuries, right? It's an important part of explaining abstract things, abstract ideas. But while there's been a whole lot of work on automating parts of mathematics, there's been virtually no work on automating the choice of good examples. But here we have a way of doing it. So what do I think is important about what we've done? Well, we found an initial approach to generating examples from formal specification. I'm sure a lot more work will be needed. But we have an initial idea. We have a method of measuring how well we've improved people's understanding. And to begin with, it wasn't at all obvious how to do that. So I think that's also a contribution of our work. And then finally, we've applied the method to our initial approach, and we have convincing proof that the heuristics really do help. And that's all I got for you.
Okay, questions?
Not so much a question, but I can definitely concur with the example part. We had, I used to work for a math education company, and not only did we spend a lot of time writing the problems, we also spent a lot of time thinking about both the correct and the incorrect answers. Because if you craft your incorrect answers, I think the industry term is detractors, correctly, then you can almost try to infer what somebody was thinking or what steps they did to get that kind of incorrect answer. So, good examples.
Interesting.
So you used college students for this?
Yes, we had students who were taking a course in parallel functional programming. About half of it was using Erlang. So they were familiar with Erlang, although these examples are simple enough that I think anybody who understands what an API is will be able to have a crack at answering questions.
Yeah, I was wondering if you had any plans to do different groups, like possibly less skilled programmers, and see if the effect was larger.
So I think what we would like to do is to scale up the method so that it's applicable to more complex APIs. The ones that we've used are fairly simple. We've been able to apply it to a number of Erlang libraries, but I think there's more work to be done. And then it would be really interesting to try different groups of people. I think the same kind of experiment can be repeated many times, which would give really interesting results.
One observation, there was a talk yesterday afternoon at Strangelip by Chris Martins, and one of the first part of her talk was about building mental models, and her examples were with respect to game environments or game worlds, and building a mental model of how that works and how you go about, she called it a mental model alignment. And so then she led a trail of breadcrumbs to a lot of research on how mental model alignment as a theory might work and how to test it, and maybe that would be useful for a similar sort of evaluation for this kind of example building.
Yes, so that brings me to a suggestion that we've had many times, which is why not take a machine learning algorithm and give it the examples and see whether it learns better given our examples than given a different kind like coverage ones. So I think that would be a very interesting thing to do. But the danger there is that machine learning requires very much more data than a person. For a person, it's a good thing if the set of examples is small. For machine learning, you would rather have hundreds of thousands of them. So you might not be measuring human learning by making that kind of experiment. It's still interesting to do, but there's a caveat there.
Do you have an idea what this would look like when you
start to show examples for distributed.
Oh, ooh.
Examples for what? Distributed computing. You know, like do something on this node and do something on this node. And how would that?
Yeah, there's a whole universe of exciting application areas out there, and I think distributed computing would be a very interesting one to address. We haven't thought about that at all yet.
Yeah, have you thought about doing the inverse thing and see how far you can go generating the spec from a set of good examples?
I have dreamt of it. So I think that would be really, really useful, perhaps, to be able to generate an initial version of the spec that you then work further with. So if you can synthesize readable code from a set of examples, I think that could be very useful, very valuable. But I haven't done it yet.
So, the question is about that when you write a quick text specification, you often put there extra assumptions on how this API works. So, for example, in the process register, the name of the process can be an atom except undefined. So, you typically write a generator that just returns atoms for the processing. But this will not give the user any examples when I try to register with a name like this. Or I may use a generator that returns arbitrary terms, then I risk that I will fool the users with examples where registering a process with a list name won't work, a binary name won't work, a reference won't work, and so on and so on. So do you have any experience on how this works with your method? So how can you constrain the usefulness of this?
Well, yes, that's a very good point. So one thing to say, I suppose, is that the spec that we used was not written for this experiment. It was one that was pre-existing, not so much for testing the registry, but because it's very good for training. So, so the spec was not tailored to example generation. And I suppose I could say, well, the title of our paper is Understanding a Spec. And the spec already has made a choice that we're going to limit registered names to atoms. In fact, they're limited to A, B, C, D, and E. And that choice is then reflected in the examples that we generate. Of course, I could write a spec that would also generate bad registered names, and then I would be able to generate this kind of example as well. The heuristics might need refinement to do that. I haven't actually tried it, but it would be possible. I guess the question is, what set of examples do you want to see? I mean, if you have a reasonable idea of what these things do, perhaps it's enough to see the successful examples that actually use atoms, rather than all of the ways you can pass the wrong type of argument. Make sense? Sort of.
Okay, well, go for it. Maybe that's
Yeah, I was curious if you've thought through, like, in Elixir, the doc test model, have you thought about how you might fold something like this in so that it would be truly part of the docs, the usage, and also executable? And I don't know if that's a path you've looked at, because then you definitely have the idea of the teaching how to use it example side, and also I don't know if there's any territory where that like if it's just API kind of side, maybe that breaks down and it's not enough coverage to get it across, but there's got to be something that hasn't been some kind of generative doc thing where you can leverage both sides of it. It feels like.
Yeah, so I think one obvious application for examples is in documentation.
Yeah.
But I'm not sure whether you would want to try and rebuild that every time, because when you present an example, you also say something about it.
Right.
And we don't know how to generate the explanations. So you might run the example generation once, and then take those examples and write some documentation around them.
Yeah.
It might also be tricky to figure out which function that a particular example belongs to, because there's several functions in the example, and is this really demonstrating this one or that one?
Yes, so in the minimal examples, it's always the last call. The last call is always relevant. And before that, generally speaking, you have one call, we're illustrating its interaction with the last one, and then the others are there to set things up, so that you can do that. So you always know that the last one is relevant. And when we gave the set of examples to students, we actually sorted them on the last call, so we labeled them, so there'd be a collection of where is examples that show how where is this used and behaves in various contexts, and so on. So it is important to do that, to make a large set of examples something that you can quickly refer to. But I think we have quite a good solution.
Thank you again, speaker.